This morning we are going to go through a special file that I have prepared for you to make it a general template that you can use to obtain any transfer function in symbolic form once you have obtained the differential equations of the system. This is going to contribute towards the block diagram method, as I called it, because we have two methods, the block diagram method or the bond graph method, which is the automated method. So in this case, we're dealing strictly with the equations of the system, the application of the Laplace transform, and obtaining the transfer functions. So let's take a look at this file and learn from it. So let me disappear from here. Okay, here we go. We have we're going to go statement by statement in here. This is a circuit where we are going to we're going to see the application of the differential equations and now strictly how to obtain the transfer function. So what I would do is my explanation is, because I want to explain the file, it's almost like reverse engineering. We're going to start with the matrix, and then we are going to see where this matrix came from. Because what happens in here is that we have definitions of symbolic variables. In other words, this thing in here says clear the workspace. Then more on means do not execute everything at once and fly by me. By allowing just to display a few lines of the output, I'll be able to digest it and read it better. That's what that is. Then we are using the symbolic toolbox in here. The symbolic toolbox, and we're defining all these variables in here. C, R, I, V, S, and L. And then the first thing is, because it has two variables, the Q1 and Q sub 2, we first have to put the system of equations in the form that in the matrix form. So what am I saying? I am saying that if you have it like this, that you are gonna put it side by side. Maybe that's a good idea. See right here, and then we'll go to my notes and also do it side by side so that I can write on this other side. What am I saying here? So let's put a title to this. We're gonna say transfer function by matrix inversion. Okay, so here's the matrix that we start. In here you have this matrix like this. This thing is saying define the first row. When you see it like this, it says do number 1 and then whatever follows. So this is V like this, and this will be minus 1 over C. Okay, that's the first row. And then you have the second row in here, yeah, This is 0, and you have it like this: 1 over c plus L times S squared, like that. Yeah? And then we are going to define the denominator. This basically is, as one of you mentioned a few moments ago, how do you actually, using Kramer's rule, how you find Q1 in this case. So this is, the denominator is defined as S times R plus 1 over C, and in here's minus 1 over C. And then the second row is minus 1 over C, and then you have this, you have 1 divided by C plus LS squared, like this. Okay, this is from a set of equations where we are trying to find Q1. It says Q1 of S. That's the statement that I made over here. See, find Q1, and then for finding Q2, I'm just gonna make it the same the same way as I did over here. So all I need is a little bit more of the space. Let me see if I can go down. Yes, I can. So in here you have Q sub 2 of S is equal, and then you have it. Do you see what I'm trying to do? Like what you were asking me about Kramer's rule is solving Kramer's rule. It's using Kramer's rule, but on using Matlab. So this is S times R plus 1 over C in here. Here you have B like this, and then you have minus 1 over C, and then 0. And then we're gonna have the denominator is gonna be the same. Okay? And here you say the determinant of the numerator divided by the determinant of the denominator. That's how we you do Kramer's rule, no? So just to make sure that everybody's on the same page, you say the denominator is the same for both of them, and that's stated over here. So if you don't remember how to enter these determinants in Matlab, now you will. So this is R plus 1 over C, then minus 1 over C, and then you have minus, and then this is 1 over C plus LS square. See, okay. This is what we are solving, but we are not doing it by hand. Do you see what I mean? At this point, by this template that I give you, if you have a 3 by 3, you would enter another row over here and another one over here. And if you have 4 or 5, just keep adding. So if you have it this way, then this statement here does exactly what's on the right hand side over here. Okay? And if you because we're going backwards, we're trying to explain the file. What are the equations that this came from? You could very clearly see that you have this set of equations like this. You have that S times R plus 1 over C. This is multiplied by Q1 of S. And then minus 1 over C times Q sub 2 of S, like this. And then we'll see this on the first equation is this is equals to the B that you see in there, like that. And the second equation that you have is minus 1 over C times Q1 of S minus 1 over C plus LS squared, like this. And then Q sub 2 equals 0. So now that we went back to the equations, I am starting from the point of view, from the point where I have applied the Laplace transform, and I just want to find these transfer functions. Okay, and so when you have the equations like this, you put them into the matrix form in such a way that you can find by using Cramer's rule or using matrix inversion, you could find this. Okay, so another way the top is Cramer's rule, but isn't it true that, let me just go here for a moment in here, that this matrix that you see in here, let me make the fundamental argument. This thing is like A times Q1 of S plus B times Q2 of S is equal to, let's call it the constant, let's call it C1. Yeah. And then the second one is like C times Q1 of S plus D times Q sub 2 of S equals to C2. Yeah? Okay. This what you're seeing here on the bottom is the sorry. What you see on the bottom is the format of this. So if we have this, we could use another method that we learn in algebra to solve this kind of things. Because if we put it into matrix form, what you have basically is this. You have that A and B and C and D, and then you have Q1 and Q sub 2 in vector form like this equals to C1 and C sub 2. But you can say, but if you multiply both sides by the inverse, we have, okay, you'll have that multiply by A, B, C, and D inverse, and then multiply by A, B, C, and D, and then you have Q1 and Q sub 2 like this. Multiply the other side also by the inverse of this, yeah, and then C sub 1 and C sub 2. But you see in here, what happens is that you have the result is of this operation that we just did, that this thing is the identity matrix, right? So therefore Q sub 1 and Q sub 2 in vector form like this should be the inverse of A, B, C, and D multiplied by C sub 1 and C sub 2. So this is the solution. Just like we did with Kramer's rule, you could do it with matrix inversion. But the beauty of this file that I'm giving you, of this template, is that you could use Kramer's rule, or you could use matrix inversion once you define this the way you have it defined in there. So let's go on to see if we find the solution here. Find the transfer function for B sub C is the voltage on the capacitor. Here you have that the voltage is 1 over C times Q1, 1 over C times Q sub 2. So in here I have used first of all I need to put it in a nice way. So you use this collect, means make it simple, collect all the terms, and then simplify. The new version of Matlab does not like this statement called simple. This, we did it with the previous version. So put a comment in here, a percentage sign. And then what you're going to do is find the ratio, make the ratio between B sub C and then V, yeah? So, okay. So let's analyze the result up to here, okay? I am going to run the file. What does it say? To run this file, you must change the current folder. I would say yes, please do that. All right. So it's a general solution. First, defines the numerator. Nobody is asked this question, but I'm going to volunteer. Why do we need this? Let's go back over here. Huh? See here, this statement here. Anybody?
I even looked at the help for SB. I don't know what it means.
Okay. Matlab doesn't know anything that you're doing operations with symbols. And so when you define a matrix, which is what I'm doing here to define the first row, the matrix of the first numerator that you see, it needs to know that it's symbolic. So this is a trick to force Matlab to produce a symbolic matrix. once it's initialized, you see the very next statement is a repeat, but now with the symbols that I want. Do you see what I mean? That's all it's going on in here. So that's what it does. See? And then that's the first one. See right there? That's what this is. And then it's going to do the second one right here. And then there's the matrix. And this one, as you see on the Matlab, is exactly this. Where are the equations? Right here. You see, right here. This set of equations. In fact, this one is the numerator, right? So is this one right here, right there. And then let's keep going. The denominator, same thing. We do those definitions, and now where are we here? The denominator one is this one, and then we have this. This C is a little farther down, the calculation right there. So this one, you see how it calculated the transfer function in here? Yeah. And there's Q2. And there's V sub C. And you can see now the transfer function of V sub C. So, and then we have the total transfer function, LS over, this is the transfer function. Okay. So if you go down, we are finding another transfer function for V sub R. And then you find the numerator, the denominator, and see how this statements that I have in here, they are suppressed because they are not numbers. I am working with symbols. And all I want are those two transfer functions. So this is what I need. So if I move it up, now that you understand the statements, I don't need to look at those more, but rather this, see. So this is the one transfer function I am looking for. This is the other transfer function that I am looking for. Right, where is it? Yeah, here, B sub C. This is the transfer function, and put it in a pretty form. This is what we see. And the other transfer function is this one. Okay, so now you understand how to solve the system of equations using Kramer's rule in symbolic form to find the transfer function. This is what we do here. So we can compare this using using the bond graph method, and we'll obtain the same thing. Okay. So let's stop there.